So this lesson covers logarithmic decrements. The logarithmic decrement represents a rate at which the amplitude of free damped vibration decreases and is defined as a natural log of the ratio of any two successive amplitudes. So the ratio of x2 to x1 is something that is what the logarithmic decrement is referring to. On the right here, we just have a diagram of x of t, or the velocity versus time, distance, or displacement, and you can see for the overdamped case, you follow this path. For the critically damped critically damped case, you follow this path. And for the underdamped, which we're referring to with the logarithmic decrement, is the path you follow here. So just to take this to a whiteboard for a second, again, it's the rate at which of decrease for free damped vibe and the ratio of two successive peaks, so x1 over x2. But if you remember from vector notation, x1 over x2, so x1 is equal to x naught e negative psi omega n t1 cos omega n t1 minus phi naught over x2, which is equal to x naught e to the negative psi omega n t2. So t2 would be this over here, and this here is t1. So we've gone forward one period minus phi naught. But if you remember, t2 is equal to t1 plus tau d. And this is the period of damped vibration. And tau d, just put a comma here, is equal to 2 pi over omega d, which is equal to 2 pi omega n over omega n 1 minus psi squared. So if you think about it, cos omega d t2 minus phi naught equals cos omega n t1 minus phi naught plus 2 pi. And cos of any value plus 2 pi is just the cos of the value. So if you really think about it for a second, if you go back up here, these two terms cross out because we're just looking one period forward. So as a result, we can cross these terms out, and we're left with just these e terms. Okay, so let's write that out here. So x1 over x2, given these relations here, is equal to e to the negative psi omega n t1 over e to the negative psi omega n t2, which is equal to e to the negative psi omega n t1, 1 over e to the negative psi omega n t1 plus tau d. And this is all to the exponent. And if you do the math, this equals e to the negative psi omega n tau d. And I actually believe this becomes a positive. Yeah, that becomes a positive. So the logarithmic decrement, delta, is equal to the ln of x1 over x2. And recall, if you take the log of something to e, you're just left with the exponent term on the e. So that equals psi omega n tau d. And here's where we get into some pretty interesting math. But if you think about it, psi omega n tau d is equal to psi omega n 2 pi over square root of 1 minus psi squared all this times omega n, which equals, if I go over here, 2 pi psi over 1 minus psi squared square root, which ultimately equals 2 pi over omega d times c over 2m. Now let me just go back for a second to clean this up. I'm going to move this a little more over here. And so you can see these omega n's cross out, your psi carries over, your 2 pi carries over, and you're left with this. But how do we get to here? Well, recall that psi is equal to c over cc, and cc is equal to 2 omega n m. And you can go through a very long exercise of substitutions to show that this relationship here eventually comes down to this. So a couple of interesting things come out of this. So psi is equal to 2 pi delta. This delta term here, the logarithmic decrement, is equal to 2 pi psi over the square root of 1 minus psi squared. But for very small psi, this term goes to basically 0, and then it simplifies to 2 pi psi. So what that's saying basically is if we know the rate at which something of a damped free vibration system is decreasing, then we can estimate psi from this term here, the delta term, or the logarithmic decrement. And we do that by basically just saying psi is equal to delta over 2 pi. So I'm just going to circle this relationship here as being a pretty important one as a way to experimentally determine psi. Now if we look at this relationship over here again, if we go here again, delta equals 2 pi psi over 1 minus psi squared. So you can isolate psi here if you square both sides. So delta squared equals 2 pi psi squared over 1 minus psi squared. And if you start to isolate, so delta squared minus delta squared psi squared equals 2 pi psi squared. What you can eventually get down to, if you isolate for psi is equal to delta over the square root of 2 pi squared plus the logarithmic decrement squared. So again, here's another expression for how to experimentally determine psi from the measurement of a system, measuring the response of a system. So the other thing this can be extended to is as many possible successive amplitudes. So if we can say x1 over xm plus 1, and you think about that, that's x1 over x2 times x2 over x3 times x3 over x4 dot 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 goes to xm over xm plus 1. So let me just clean this up again. So this is x. So you're left with all these x terms. This crosses out with this crosses out with this, and you're just left with xm over xm. And now that I've written that, I realize that's not exactly correct. So this is x1 actually. Oops. x1. So if you think about that for a second in terms of, so it's x1 over xm plus 1 equals really e psi omega n tau d, and this is to the times m. So that equals e m psi omega n tau d. Or if you take the log and isolate for delta, delta equals 1 over m ln x1 over xm plus 1. So again, this would apply to any number of successive amplitudes where you have x1 and xm plus 1. So with these equations, you can start to solve problems. And just to go over, I'm always good for making a couple of mistakes. Really, if you look here, I should have written equals, eventually equals this term right here. If we scroll up here, I believe I should have wrote squared here. Is that correct? So delta squared, yeah. So put a squared term here, and then put a squared term here, and that squared is carried down there. And then, if you think about it for a second, this omega d is actually omega n. So it's omega n t2. Let me just clean that up. So yes, omega n t2 minus phi naught is equal to this. And I think everything else, actually one more thing here, this should be in brackets because that's time. So these terms here should be multiplied by t1 plus tau d. And I think that's it. And actually the one other thing I think worth mentioning is this is for when psi is really small. So would it be psi is much greater than 1. And this relationship here is when you can't have this, you have to be worried about psi. Or you can't make the substitution where this term here drops out. So then here's the other relationship when this doesn't apply down here. And I think that should be it.